Alright, welcome back ladies and gentlemen. Today we're talking about the assume mode method. This method is very appropriate anytime you have dynamical systems that have distributed masses and continuous masses. So I've drawn this example here where I have a simply supported beam with lateral deformation V as a function of x, which is the position along the span of my beam, and the time variable t. In the past, what we've done has been to take our beam and discretize it such that we have a number of lumped elements, and this is really what the method of finite elements is like. You're lumping your performances into a bunch of discretized versions of your original self. And so then we would have these degrees of freedom, 1, 2, and 3, describing the motion of our beam. Now with the assume mode method, we do things a little bit differently, where we would have to make assumptions with regards to the shape of our modes. So if you are someone who has dealt with the performance of a simply supported beam, you would know that your first mode would have to look like this psi 1 here. Psi 1 is the first mode shape, and it's going to look like a sagged cable almost. And you would also know that your second mode is going to have this S shape to it, and it's marked by psi 2. And so in this lecture we're going to talk about axial elements, and we're going to talk about flexural elements. In the case of axial elements, deformations are U, xt, and they equal the sum of individual mode performances. So we have I, N, and these performances include the mode shape, which is a function of x being the position along the beam, multiplied by the performance of that mode shape. So we're going to have U, I, and U is going to be, UI is going to be a function of time. In the case of flexural elements, we're dealing with lateral deformations, so we're going to have V, X, T, and that's going to be equal to the sum of, we're going to have a similar structure as to before, so we're going to have psi, I, X, and this time instead of axial deformations for each mode, we're going to have lateral deformations for each mode, and that's also going to be equal to or a function of time. Now, when we're selecting these psi functions, we have to look for admissible functions that meet conditions like the boundary conditions and so forth. And what I like to do now is to list a number of conditions for admissible functions. So we want to do conditions for admissible functions. And these functions are the shape functions, size. First of all, these functions need to be linearly independent. So anytime we have a dynamical system which we're modeling with multiple shape functions, these shape functions need to be linearly independent. Now, what does that mean? It means that if I have a shape function psi 1 and if I have a shape function psi 2, then I'm not going to find an alpha and a beta that make this sum equal to 0. That's not going to happen. An example of this is x and x squared. Except for the position x is equal to 0, you're not going to have any other cases where these two are going to somehow equal to 0 for a continuous span of x's. Alright, now what is the second requirement? The second requirement is that the shape function must possess derivatives up to the order seen in the strain energy. Now I'll explain in a second what that means. Anytime you're thinking about strain, you're also thinking about deformations. So we can have different kinds of deformations. Let's think about this cantilever here, and I'm pushing down on this cantilever. Is this cantilever going to have displacements in the downwards direction? Yes. So when I'm selecting my psi function, it needs to vary with x. Okay, that's the first requirement. That's the first element in the strain energy requirement. Now, when I'm deforming this beam downwards, is it going to have a slope? Yes. Is that slope going to vary with position x along the span of this beam? Yes. So psi prime x also needs to be a function of x. Now, the next derivative in this list of strain energies will be curvature. The second derivative, I want to say, is curvature. Now, curvature is proportional to the moment divided by the elastic modulus and the moment of inertia. Now, if I have a loading setup which results in moment that is not constant or that is not zero, then I need to have a mode shape that describes that kind of that kind of curvature. So let's think about this. Let's say I have psi that is equal to x over L cubed. Then I have psi x. It's satisfied. This is satisfying the deformations. So deformation is varying with the position x. If I'm thinking about psi prime x, then I'm thinking about 3x squared over L cubed. Then yes, my slope is also varying with position x, and I'm also thinking about my curvature. Yes, that one's also changing with position x, and it's not constant or zero or anything. So curvature is satisfied as well. And these are things you need to think about. Now, if you don't have moments or if you don't have slopes, then you don't need to go as high as the third order. Perhaps a first order function would satisfy. Okay, so the most important thing here was to satisfy strain energy. All right, what's number 3? Number 3 is boundary conditions. If I have a cantilever like that, and I'm pushing down on it, then at position 0, assuming I'm measuring x like that, psi 0 must equal to 0, because when I have a fixed position, I'm not going to have any deformations at the location of the fixed position. And at the same time, I'm not going to have any slopester. So psi prime is equal to 0. So anytime these 3 conditions are satisfied, then I have an admissible shape function that I can use to do my analysis. And most likely, I'll get a pretty good answer. Now, I like to make notes of something. Derivatives. In this particular lecture, we're going to be dealing with 2 different kinds of derivatives. If I have a function p and I put a prime over it, what that means is I am taking derivatives with regards to position x. Now, if I put a little circle or dot on it, it means that I'm taking derivatives with regards to time. So keep that in mind as we proceed. All right, so let's talk about axial elements. I'm going to draw this axial element, and I'm also going to give it a boundary condition, which is a fixed boundary condition. And this axial element is to be subjected to an axial force P, and we're going to measure x from the base, and we're going to measure the axial deformations by u, and they're going to be functions of x and time. All right. Now, what is this question asking us? We're doing an example here. Example. The first thing we need to do is to to identify our equation of motion. So find the equation of motion. That is the most important thing we need to find out. And we need to find the equation of motion we need to specify the location along this axial elements where we're finding the equation of motion for. So the equation of motion is being found with regards to this tip here, the tip of my axial element. And the question is also asking us to use two mode shapes to do this process. Two mode shapes. And so I first need to identify what my boundary conditions are, and there's really just one. Psi 0 is, psi 0 is equal to 0. So I have no deformations at the base. And having said that, I'm going to introduce two shape functions that satisfy this boundary condition, and ones that I think are suitable for this problem. The first one is x over L. The second one is x over L squared. I will take the derivatives of these with reference to x because we're going to use these later in the problem. So psi 1 prime of x is equal to 1 over L, and sine 2 prime of x is equal to 2x over L squared. Now we're going to take advantage of these and do some math with these later. All right. Now, how do we go about solving a problem using the method of assumed modes? The answer to that is virtual work. Virtual work. We're gonna introduce a couple of relationships that describe the energy in our system, externally applied energy and the internal energies, and we make them equal, and because total energy is always equal to 0. Anytime you're dealing with the method of virtual work, you're thinking about energies that are equal to 0, the sum of energies that are equal to 0. So we introduce this variable delta. It comes from an area of mathematics called the calculus of variations. So we have the variation in energy is equal to the variation in non-conservative energy. NC, non-conservative energies are all the externally applied energies, and then we have the variation in potential and variation in kinetic energy, and these two are the conservative energies, and they have to equal to 0. Okay, and so let's talk about kinetic energy and how it's equal to the forces we have multiplied by the virtual deformations we have. And in the case of this axial elements, we're interested in this integral. And so when I plug in the solution for the forces, we get the following. I have rho, which is the density of my material. I have A, which is my area. I have U dot dot, which is my total performance. And I have a delta U. And then I also introduce a dx because we have to integrate over the position x. And so the next thing I'll do is to pull my rho and A out because they're not functions of x. Rho and A are pulled out. Then I have my integral. This term here is going to be a column vector, and this term here is going to be a row vector. So I will have x over L. This is my psi multiplied by the performance of my first mode, I have x squared over L squared multiplied by the performance of my second mode. If you recall, U is equal to psi I U I, and that's what we're plugging into here. And then I have my row vectors, where the first one is x over L delta U 1. Then I have x squared over L squared. Then I have a delta U2, and then dx. All right, now let's multiply these two vectors, and we're going to have the following setup. We're going to have x squared over L squared, x cubed over L cubed. It's going to be symmetric. And then x4 over L4. Then I pull my ui's out, put them here, and I pull my delta u's out and put them here. And lastly, I have my dx, which culminates my integral. And now we do the mathematics, and we end up with rho a L, 1 over 3, 1 over 4, 1 over 4, and 1 over 5. What you've noticed is that what we're doing here is identifying our mass matrix for the equation of motion. And this is really how we do it for this new method. All right, that's the inertial component, and it is taken care of. What are we going to do next? So we have to look at our virtual energy equation, and the next term I would say is the potential energy. So let's do delta V. All right, as it turns out, delta V is equal to the following: elastic modulus area U prime delta U prime dx. All right, let's plug parameters in. I pulled the E and A out of the integral because they're not functions of x, they're constants. What I get is 1 over L, 2x over L squared. And I should also put a U1 here, and a U2 here. Okay, so what we have, this is our column vector. Again, this term is going to be column vector, and this term here is going to be a row vector. So we have 1 over L, delta U1. We have 2x over L squared, and that's a delta U2. Then we have dx. So I'll jump 1 or 2 steps and jump right into the conclusion, and I'll have the following stiffness matrix: 1, 1, and 4 over 3. We have ui, which is a vector that contains u1 and u2, and it's pulled out of the integral. And I have a delta ui, which are the delta u1s and the delta u2s. These are also vectors, and they're pulled out. The last thing we want to look at is our non-conservative forces. So we have delta non-conservative. And because the force is affecting both of the modes, modes 1 and 2, we're going to have a column vector PT. This column vector is multiplied by delta U, which is again the virtual deformation. And because delta U at position L is where these forces are getting applied, is equal to psi L delta UI L. I should probably, I'm hitting the margins of my paper, I should probably write these a little bit inwards. So write them here. There we go. So we have delta U at position L is equal to psi at position L multiplied by delta UI at position L. So all these psi's at position L are equal to 1. So I have PT, PT, then I have a delta UI. So that's what I end up with. The next thing I need to do is to say that delta W star is equal to 0, so the variation in energy is going to equal to 0 in my system. So what I'll have is PT, PT, this is a column vector minus the stiffness term because the inertial term is always counteracting the stiffness term, we have to put a minus here. So whatever whatever forces we got, we minus that. So we have rho AL 1/3, 1/4. And looks like I missed a term here. I think this should be a UI. Okay, and then we have UI double derivative, and now we close the brackets, and we have the delta UI here on the outside, and that's equals to 0. We know that this term is not going to be equal to 0. That's the arbitrary solution, so we're only going to be focused on the term here on the left, this whole term. So what we end up with is rho AL, the matrix, and then I have the stiffness term. So clearly with this example we don't have damping and we're dealing with an undamped system, and that's okay. Damping is not going to make things any more different than we have it now. And this whole thing is equal to the forces. Okay, that's really it. That's our equation of motion, and this question is completed. Now we're going to focus on flexural elements. So let's talk about flexure. Okay, so potential energy, here we come. We have delta V is equal to integral 0 to L. We got the elastic modulus. This time, because we're dealing with lateral deformation, we're dealing with the moment of inertia. In the last example, we dealt with areas. This time, it's the moment of inertia. So we have V double prime, delta V double prime. Again, when we mentioned the V double prime, we're always thinking about the curvature. So we're thinking about curvatures in the potential energy strain energy equation, and that's what we have. Now again, we plug and play. We pull the EI out. L 0. We got 2L squared. We got another 2L squared that we're multiplying together, and we got the dx's, and then the VI and delta VI. And then we just wrap up this integral, and we end up with 4 EI over L cubed. we got VI, and we got delta VI. Now at this position, we should be done with this problem, and we would typically write out our equation of motion and be finished with it. But there is another thing I'd like to add to this analysis, and this thing we refer to by as geometric stiffness. So what is geometric stiffness? If you go back to the diagram that we drew earlier and think about what would happen if this mass at the very tip were to bend. So we have this column bending, and this lump mass at the very tip is now out of position, and there's also the gravitational pull on it, and we got a magnitude g. So the more that this mass bends, the more bending effect this column is gonna feel from the combined effect of the mass and the gravity. So now think about this mass elongated around a different position. So it's bending even more, and now there is going to be a bigger moment arm about the base of this column structure. And so what's really happening is that the mass and the gravity are reducing the stiffness of our column just because of the combined effect that they're having on the stiffness term for this column. And we call this geometric stiffness, and geometric stiffness tends to reduce actual stiffnesses of columns. And this holds true anytime you have columns that are very tall and slender and they are holding up big masses. And so the relationship for geometric stiffness is described by Kg is equal to integral Nx. Nx is the force that is being applied by the mass of the structure. In this case, we're interested in the tip mass. And then we have psi prime x, delta sine prime x, dx. So that's really what we're interested in. And the force that is being applied by the tip mass here is described by mg. And I plug in the rest of this equation in, and I have 2x over L squared dx. And so when we complete the math, we should end up with 4mg 3L. So that's what we end up with. Now, the new stiffness term that we're going to have for this column structure, this cantilever, is going to equal the original K minus the geometric stiffness. Okay, so this whole thing is equal to 4EI over L cubed minus 3mg over, excuse me, that's 4mg. 4mg over 3L. We got V I plus rho AL over 5 plus M. That's what we have. And then we're closing these brackets, and we have our variation term, and that equals to 0. And so clearly this term here is not going to equal to 0. That is the arbitrary solution. What I can say is 4EI over L cubed minus 4mg 3L. We only have a single mode here, so V1 plus rho AL then we have V1 double dot is equal to 0. And that's it. That's our equation of motion. All right, I hope you found this lecture useful. This kind of analysis is very useful anytime you're dealing with distributed masses. So, you can just think about the number of applications you can solve with this kind of approach. And yeah, I will see you in the next lecture.